All right, let's just jump right in. Black holes, they are, without a doubt, some of the most mind-bending things in the entire universe. We're talking about places where physics gets so incredibly strange, it can literally change the way you think about reality itself. And the wildest part? The math behind them, this really solid math, is being proven right by what we're actually seeing out there in space. So let's go explore the unexplorable. So, the very first thing we have to do right off the bat is just throw out our whole idea of what a black hole even is. I mean, we call them holes, right? But that's not really what they are. The truth is much, much weirder than that. And here it is. This is the absolute key. A black hole isn't a thing. It's a place. It's a region in space where the very fabric of space and time is bent and warped so severely by gravity that it basically creates this cosmic trap. And if you can get your head around that one idea, it is the key to understanding everything else we're going to talk about. So, to really understand this warped reality, we kind of have to go back to its violent beginning. Let's take a look at how these massive shadows on the universe are actually born. Okay, so it all starts with the death of a truly massive star. I mean, a real giant. For most of its life, a star is in this perfect cosmic balancing act, right? You've got the outward push of nuclear fusion fighting against the inward crush of its own gravity. But when a really big star starts to run out of fuel, that fight is over. It fuses heavier and heavier elements until it gets to iron. And that's the big problem. Fusing iron doesn't release any energy, so that outward push just stops. And gravity wins catastrophically. The core collapses, it rebounds, and triggers this spectacular explosion, a supernova, leaving behind this hyper-dense remnant. Now, what's left behind? Well, the star's fate really just hangs in the balance. If the star was massive, you get a neutron star. Think of a ball of matter the size of a city that's so dense a single teaspoon of it would weigh 1 billion tons. Just insane. But if the star was extremely massive, the collapse is so total that physics as we know it just, well, it breaks. All of that mass gets crushed down into an infinitely small, infinitely dense point. We call that a singularity. And this is where things go from just, incredibly massive to truly bizarre. Because when you warp space-time this much, you're not just messing with space, you're messing with time itself. So, around this singularity is a boundary called the event horizon. Now, this isn't a physical surface you could touch. Think of it as the ultimate point of no return. The black sphere you always see in pictures, that's not the black hole. That's this invisible border, the event horizon, where the escape velocity becomes faster than the speed of light. And since nothing can go faster than light, nothing gets out, period. And this is where time itself just completely splits in two, depending on where you're watching from. It's wild. So if you stayed a safe distance away and watched your friend fall towards the event horizon, you'd see them get slower and slower and redder and dimmer until they just seemed to freeze at the edge forever. But for them, for your friend crossing that line, time outside would speed up so dramatically that they could witness the entire future of the cosmos flash before their eyes in a single moment. So, it's an inescapable prison. Nothing can ever leave. Case closed. Right? Well, not so fast. In 1974, Stephen Hawking came along and basically said, hold on a second, not exactly. And this is the great paradox, isn't it? If the event horizon is a one-way door, how on earth can a black hole possibly lose mass and, well, evaporate? The answer, it turns out, isn't found in gravity. It's found in the super weird rules of the quantum world. To get our heads around this, we have to think about nothing in a totally different way. See, according to quantum physics, empty space isn't really empty at all. It's this seething, bubbling foam of invisible, vibrating energy fields. You can think of them as the fundamental fabric of reality itself. Now, because of a weird rule called the uncertainty principle, these quantum fields are always fluctuating. And for these incredibly brief moments, these fluctuations can actually borrow a tiny bit of energy from the vacuum to create a pair of virtual particles, one made of matter, one of antimatter. But they have to pay the loan back, so they almost instantly collide and vanish, balancing the cosmic books. Okay, but what if this little particle pair pops into existence right on the razor's edge of an event horizon? Well, it's possible for one particle to fall in while the other one escapes. Suddenly, the escaping particle can't annihilate its partner anymore, so it becomes a real particle flying off into space.
And that faint glow of escaping particles, that is what we call Hawking radiation. And here's the kicker. Because energy can't just be created from nothing, the black hole has to pay for that escaped particle. The energy is stolen directly from the black hole's own mass. I absolutely love this analogy from the source material. It's not that anything is actually escaping the bank vault. It's just that the universe is balancing its books in a very, very strange way. And over billions, trillions of years, this slow leak will cause the black hole to evaporate completely. So we find out black holes are not just cosmic destroyers or these leaky prisons. In a really strange twist, they're also some of the most powerful and creative engines in the entire universe. You see, because things in space are already moving, they almost never fall straight into a black hole. Instead, their momentum makes them spiral inwards, piling up into this flat, spinning, super hot structure called an accretion disk. And as all that gas and dust and star stuff gets squeezed and accelerated to near light speed, the friction is just unbelievable.
How unbelievable! Well, the brightest of these accretion disks, we call them quasars, can generate so much light and energy that they can outshine our entire Milky Way galaxy, with its hundreds of billions of stars 1,000 times over. Think about that. A single black hole powering that. It's just staggering.
So you see, black holes are so much more than just cosmic voids. Their accretion disks are these brilliant beacons we can see across the cosmos. The intense conditions inside them forge new elements. They launch these colossal jets of particles from their poles that can stretch for millions of light years, seeding the universe with new material and actually shaping how whole galaxies evolve. They are, in a very real sense, fundamental architects of the cosmos.
And all of this leaves us with one final, fascinating thought to chew on. We tend to think of our mass, our reality, as the thing that bends space-time. We're the foot that makes the footprint in the sand. But the weird physics of black holes suggests that maybe, just maybe, the relationship is the other way around. What if space-time curvature is the really fundamental thing, and we, our very existence, are just the shadows it casts on the wall of the universe? It's a question that really shows you just how deeply these cosmic mysteries can make you question everything.